We stand at a thrilling new frontier in our quest to understand the universe. Imagine computers that think in ways previously confined to science fiction. This is the dawn of quantum AI. It is rapidly changing how we explore the cosmos. Astronomers are now armed with an incredible new tool. This tool helps them sift through mountains of data from powerful telescopes. The universe is vast and full of mysteries. Quantum AI is like a superpowered detective, ready to uncover its secrets. It promises to accelerate discovery beyond our wildest dreams, turning data into understanding at an unprecedented rate. So what exactly is this quantum AI that's causing such a stir? Think of normal computers using bits, which are like light switches, either on or off, 0 or 1. Quantum computers, however, use qubits. Qubits are far more complex. Thanks to the strange rules of quantum mechanics, they can be 0, 1, or both at the same time. This is called superposition. Furthermore, qubits can be linked together in a phenomenon called entanglement. These quantum tricks give these new computers immense processing power for certain types of problems, far exceeding classical machines. This unique power makes quantum AI exceptionally good at analyzing data. Quantum AI can spot correlations and anomalies that would otherwise remain invisible. The recent headlines about quantum AI identifying potential evidence for this elusive world are just the beginning of this new era of discovery, a tantalizing glimpse of what's to come. The astronomical community buzzed with excitement recently. News broke that quantum AI, crunching data from the James Webb Space Telescope, had helped to analyze a fascinating object known as 2017 of 201. This wasn't just any space rock, its characteristics immediately set it apart. The involvement of cutting-edge AI in understanding such a distant object highlighted how technology is pushing the boundaries of exploration. So, what is 2017 of 201? It's a minor planet, estimated to be about 700 kilometers wide. Interestingly, it's unusually bright for an object so far out, which supports the idea that it might indeed be spherical. The truly astonishing thing about 2017 of 201 is its orbit. It swings around our sun on an incredibly wide and stretched-out path, an elliptical journey that takes nearly 25,000 Earth years to complete. The records suggest its last relatively close pass to the inner solar system, though still incredibly distant from Earth, was around November 1930, a silent visitor from the deep freeze. The discovery and detailed analysis of 2017 of 201 immediately sparked discussions about Planet 9. You see, the main evidence for Planet 9 comes from a group of ETNOs whose orbits appear to be strangely clustered. Their elongated paths all point in roughly the same direction, and their orbital planes are similarly tilted. This alignment is highly unlikely to be a coincidence. It suggests that a large, unseen planet is gravitationally shepherding them. So, when a new ETNO like 2017 of 201 is studied, astronomers are keen to see if its orbit fits the pattern. However, 2017 of 201 throws a spanner in the works. Its orbit doesn't cluster with the other ETNOs that form the primary evidence for Planet 9. This is a puzzle. Despite this apparent contradiction, the detailed study of 2017 of 201 is incredibly significant. Its existence implies that there could be a hidden population of similar large objects lurking in the distant solar system. When we talk about Planet 9, two names invariably come to the forefront: Mike Brown and Konstantin Batygin. These Caltech astronomers are the modern architects of the Planet 9 hypothesis. Mike Brown is a well-known figure in planetary science, famously associated with the reclassification of Pluto to a dwarf planet. Together with Batygin, a brilliant theoretician, they have built a compelling case for a hidden giant in our cosmic backyard. The foundation of their hypothesis, first published in 2016, rests on the peculiar orbits of a handful of ETNOs. Brown and Batygin argued that this clustering is statistically significant and unlikely to be a random occurrence. They proposed it is the gravitational signature of a massive unseen planet. Their ongoing work is crucial in guiding the search and interpreting the complex dynamics of the outer solar system. The James Webb Space Telescope, or JWST, represents a monumental leap in our ability to observe the universe. Launched on Christmas Day 2021, it is the successor to the Hubble Space Telescope, but with capabilities far beyond its predecessor. Its huge primary mirror, over 6.5 meters in diameter, and its advanced instruments are designed to capture infrared light. This is crucial because the light from the most distant galaxies and from cool objects within our own solar system is stretched into infrared wavelengths by the expansion of the universe or by their low temperatures. This sensitivity to infrared light makes JWST an invaluable tool for searching for faint, distant objects in the cold outer reaches of our solar system. The recent application of JWST data in the analysis of 2017 of 201, facilitated by quantum AI, showcases the telescope's precision. Beyond characterizing known ET-NOs, there's a fervent hope that JWST might play a more direct role in the search for Planet 9 itself. The search for Planet 9 is, without a doubt, one of the most challenging astronomical hunts ever undertaken. We are looking for a world that is, by its very nature, incredibly difficult to find. If it exists as hypothesized, it is extremely far away from the sun. This means it reflects very little sunlight, making it exceedingly faint. It would also be moving very slowly against the backdrop of distant stars. Several major observational difficulties compound this challenge. Firstly, telescope time on the world's most powerful instruments is a precious and highly contested resource. Surveying the vast swaths of the sky where Planet 9 might be lurking requires an enormous amount of dedicated observation. Because direct detection is so difficult, astronomers often rely on indirect methods. Just as the challenges in finding Planet 9 seem immense, so too does the promise of new technology. A beacon of hope for astronomers eagerly hunting this elusive world is the Vera Rubin Observatory. Currently under construction in Chile, this next-generation facility is poised to revolutionize our understanding of the transient and moving universe. Its primary mission is the Legacy Survey of Space and Time, or LSST, which will involve scanning the entire visible southern sky every few nights for 10 years. The Vera Rubin Observatory's capabilities are perfectly suited for the Planet 9 search. It boasts a massive 8.4-meter primary mirror and the largest digital camera ever built, capable of capturing an area of the sky 40 times the size of the full moon in a single exposure. This combination of a wide field of view and incredible sensitivity means it will detect billions of new stars and galaxies, but crucially for us, millions of new solar system objects. It is expected to find objects much fainter and more distant than current surveys can typically reach, potentially including Planet 9 itself. The data from Rubin will be transformative. By repeatedly imaging the sky, it will allow astronomers to track the movements of countless objects with extraordinary precision. Beyond the Vera Rubin Observatory, other future telescopes and innovative techniques will undoubtedly contribute to our exploration of the outer solar system. The quest for Planet 9 is a marathon, not a sprint, driven by relentless technological innovation. In science, it's crucial to explore all plausible explanations for an observed phenomenon. While the Planet 9 hypothesis provides a compelling narrative for the strange orbits of some ET-NOs, it is not the only idea on the table. One alternative suggestion is that the gravitational influence attributed to a single large planet might instead come from a massive, extended disk of smaller icy bodies. Another set of alternative explanations looks to the past. Perhaps the current orbital configurations of ET-NOs are not due to an object that is still present, but are relics of ancient events. More exotic hypotheses have also been put forward, such as a tiny primordial black hole. While these alternatives are fascinating, the Planet 9 hypothesis often remains the most straightforward and dynamically plausible explanation for the specific type of clustering observed. The journey to understand the outermost reaches of our solar system has been invigorated by remarkable technological advancements. The synergy between the keen eye of the James Webb Space Telescope and the analytical prowess of quantum AI is already yielding fascinating insights. Finding Planet 9 would be a discovery of monumental significance. It would fundamentally alter our map of the solar system, adding a new major planetary member to the family. It would tell us that even after centuries of astronomical observation, our own cosmic neighborhood still holds profound surprises. Confirming its existence would revolutionize our understanding of how our solar system formed and evolved. The implications of discovering Planet 9, or understanding the phenomena that mimic its presence, extend far beyond our own solar system. The processes that shaped our planetary system are likely common throughout the galaxy. Ultimately, the search for Planet 9 speaks to something deep within the human spirit, our innate curiosity, and our relentless drive to explore the unknown. The grand cosmic detective story continues, and the universe still has many secrets to reveal.